In a continuation of what I showed yesterday, I would like to decode a 00 instruction. Sometimes, for whatever reason, a CPU may end up executing instructions in an area where memory is cleared, uninitialized, just consists of all zeros. And what instruction CPU ends up executing then? On many older architectures, byte 0 was just a code for nope, no operation instruction. But it is not so on x86. For x86, nope is just 90 hex. We can confirm that now. So, what does a 0 mean? We can use the hints I prepared yesterday when I was showing how octal system is a key to understanding of the old x86 encodings. So let's write it down as octal number. It is simply 3 0 digits. It should be an add instruction then. And it should be add reg8 or mem8, and second argument also reg8. So now for a second byte. Again, all zeros. This is a mod or m byte. Mode, as you may remember, 0 means memory, 1 and 2 is memory with displacement, and 3 is register. So here mode, it is the highest octal digit, 0. It means that this is just a memory operand. Register operand is 0. 8-bit register with number 0 is AO. And this one we should look at in the table. It's this one, bx plus si. Okay, let's try it. Assemble and see how it goes. Yes, it is what we expected, 0 0 0 0. But this is in 16 bits mode. what about 32-bit mode? The 8-bit operands are not affected by mode. If this was 1, then it would be affected, but for 0, this size is always 8-bit, so mode does not matter. The only place where 32-bit mode does matter is the addressing. So here, 32-bit addressing forms, 0 is EAX. Let's try it. That's right. In 32-bit mode, this instruction is all zeros. And what about 64-bit mode? (64-bit) addressing forms are very similar to 32-bit ones. The only difference is that by default they use 64-bit registers instead of 32-bit ones. So this probably should work as 64-bit register. That's right. And just to play with octal a bit more, if we, let's say, change add to addition to subtraction 0 to 5, only this single digit should be changed. To 8 hexadecimal in octal is 50. And if we change the lowest digit, then we rotate this form. Oh, let it be 2. This just changes places of 2 operands. So they should become in the reverse order. Oh, I forgot. 16-bit mode is needed for that. Alright, 2a hex is 5 to octal. As expected. Now in second byte we can change the highest digit to 1, and this is then displacement 8-bit. So any number, let's say 3, is going to generate such an instruction code. For 0 hexadecimal is 100 octal. And we have an additional byte 3. Hexadecimal 3 or octal 3 doesn't matter in this case, how we write it down. And if we change it to this variant, then we have an instruction that has a set register it operates on. So we no longer have a mother n byte. And the second byte is just the immediate value, so number 3 in this case. This is 5 for octal. Immediate in second byte. I may add O here so that it is clear that we use octal system for these numbers. So this is how you handle these basic 8 instructions. But there is more. There are other places in the x86 instruction table where octal system may be useful. Here is another row of 8 instructions. Exchange. Always with AX. All in sequence. But isn't that a code of nope that I showed earlier? This explains why nope on x86 architecture has this strange code, not 00 as on some other CPUs. They simply called exchange AX with AX nope. But this led to something interesting when we moved to 64-bit architecture. So in 32-bit mode, again, exchange EAX with EAX is still nope. But, as you may know, when we move to 64-bit world, any instruction that operates on 32-bit registers does clear the upper halves of 64-bit registers. So this is no longer a no operation. This is an instruction that does something. It does clear the upper halves of array X register. Oh, but it is assembled to a different code. Why? Well, because 9.0 was reserved for NOP, and it is still just NOP even in 64-bit mode. So if you really want to do exchange EAX with EAX in 64-bit mode, long mode, you have to use a longer code. This exchange. This is a general exchange with register and memory, but as you know, with mod equal to 3, you can change it to exchange register with register. So it is possible to generate the same instruction in this second variant. And in long mode, this instruction can only be assembled to this long form, because short form 9.0 is no longer this instruction, it is just NOP. Even rex prefix does not change that. Do you have any questions? I planned to cut it short today, so this is all I had prepared for now. Oh, are there timing penalties for using exchange to clear upper 32 bits? I don't know from memory. We would have to look it up in optimization manual. This changes from generation to generation. One more thing, in original 8086 I said it was in general octal architecture, but there are some runs of instructions that come not in 8s but in 16s conditional jump first gun. So, for example, not just 8 conditional jumps, but all 16 conditional jumps continued here. This is a long row. Oh, and another thing I did not mention is how mod_rm works when you have a single operand instruction. Something like not with a single operand. Let's look it up. F7. This is a unary group 3. This kind of instruction, the second byte is a standard mod_rm byte, but one of the fields, instead of indexing register, indexes a group of instructions. Not important, that is this number in octo. This one is more important. Okay, so mod3, it means that M is then a register, 0 means AX register, this one. What does 2 mean here? This is an index of an instruction in a unary group. F7. F7 is a group. That has not instruction as number 2. 0, 1, 2. Did I learn all of this the hard way when I wrote Phasm? Well, Phasm was not my first assembler. It was my second assembler, in fact. The first one I wrote in 1997, and I was just writing it as I was learning how to encode the instructions. You know, it was all quite simple back then. It was before we had SSE and then AVX and 64-bit architecture. Much less instructions, much less encoding variants. We'll still have an EVEX left to cover somewhere in the future. EVEX is really the culmination of x86 architecture becoming more and more complex. This is a prefix before the actual instruction code that already consists of 4 bytes of information. Have I encountered undocumented behavior when dealing with encodings? Well, some, not very important. Let's go to the opcode map. Oh, this is going to be in groups. You see this gap here? When I was writing my assembler, I saw that this is SHL, then SHR, shift left, shift right, and then arithmetic shift right. And it seemed that from the symmetry point of view, this should be arithmetic shift left. But these two instructions do the same thing. So in manual, officially, they call SAL just alternative name for the same instruction. SHL, SAL are the same instruction. But if you try to execute this undocumented instruction here, this gap, it really works the same as if it was, in fact, SAL. So there is a hidden, useless symmetry here. And another interesting example is FNN enable coprocessor interrupts and disable. This should not assemble. Yeah. These two instructions existed only in this very old variant of coprocessor. If we change to a newer one, they are no longer there. They are not documented anywhere in a modern Intel documentations, but they are still recognized as valid instructions, even by modern CPUs. They simply do nothing, but they are still recognized as valid instructions. I would like to wrap it up now, but if you have any more questions, please ask. Oh, this is a good question. If you always use 64-bit registers, so let's go back to 64-bit architecture. Compare this with a similar instruction on 32-bit registers. The instruction that uses long registers, 64-bit, needs rex prefix. So you may end up with a larger code. And larger code is, well, bad for cache, so performance may also be worse. So yes, it is better to use 32-bit registers when you can, and only use long registers when you must. Oh yes, decoder performance penalty is there also. But remember that for addressing modes, it is the opposite. If you would use 32-bit address, then you need an additional prefix. So the best variant is to use 64-bit addressing, but 32-bit arguments operands. Yes, additional prefix is not only more memory used, but also more bytes to fetch when decoding, one more byte to decode. This all can be a penalty. When I write assembly projects like FastG, I usually optimize for code size, because this is the only one optimization that is truly universal. Yes, I prefer smaller code, even if data is larger. Oh yes, of course. When you optimize for a specific generation of CPUs, then a longer code may have a much better performance. But if you want to write something universal, with no specific generation of CPUs in mind, then I would stick with size optimization, because it is the only one that is truly universal. But of course, first use good algorithms and then optimize for size. Alright, thank you all for coming, and I'm going to finish for today. Bye.